now. And thank you again for joining us. And Duane, I'll turn it over to you.
Well, thank you, Erin, and welcome everyone. I just saw from the chat box as we were going through here right before we started that a few folks may be actually experiencing some of the things we're going to be talking about here today. So hopefully everybody can stay safe. Majority of the people that registered for this, I believe, are from Illinois, but we do have a few folks from out of state, and we actually had a few registrants from out of the country. So for wherever you're at, if you're on, welcome. And we're going to go ahead and get started with this. And so what we're going to talk about, and these are things that hopefully most of you have experienced, but experienced in a good way. And this is one of the things that really got me interested in meteorology to begin with. I grew up on a farm, and I just used to love during the summertime when I would see a squall line come in and come over the farm and then go on. That just fascinated me. And that's really what got me interested in meteorology to begin with. So we're going to talk about some of those things today. We're going to talk about thunderstorms. We're going to talk about lightning. We're going to talk about tornadoes. And we'll touch a little bit on safety issues. We're also going to touch on some of the most current research on some of these things as well. So to start off with, in terms of thunderstorms, and I probably imagine that the vast majority of folks have experienced thunderstorms, but there are different categories of thunderstorms that we can talk about. We're going to talk a little bit about single cell or pop-up thunderstorms. And then there's a category called multi-cell thunderstorms. And within that, we have some subcategories of training thunderstorms, squall lines, and something that you may not have heard before is something called mesoscale convective systems. And then the third category are supercells. So to talk a little bit about a single cell thunderstorm, think about a warm summer afternoon. You're looking off in the distance. You see some of those cumulus, those puffy cotton ball shaped clouds growing higher and higher. And then eventually you see one of them get to the point where you can see some rain coming out of them, maybe a few streaks of lightning, and then they just kind of fade away. That's really what these single cell thunderstorms are. They're generated during that warm afternoon heating of the Earth's surface. And imagine these bubbles of air that are heated up right above the land surface, and then they rise up. And where they rise up, if they rise up high enough, they'll create a cloud. But if they can continue to rise, they may end up becoming a thunderstorm. And again, this is created from this convective activity that occurs during summer afternoons. So you only see them typically in the afternoon. Each one of these really don't amount to a whole lot. You may get a little bit of rain, a little bit of lightning, maybe some small hail, but then they just fade away. Now there'll be multiple cells that may pop up during the afternoon, but again, once the sun goes down, they usually fade away. Now, with any thunderstorm, you typically have 3 stages involved with it. And if we're going from left to right on this, you can see that at the beginning, what you have is that thunderstorm rising up, getting taller and taller. And that's called the towering cumulus stage. And one of the things I want to point out with this is within that stage, mostly what you have is air rising up or updrafts. And if you look down at the bottom of that cloud and you see that flat base to it, that's telling you exactly how high that air had to rise to the point where water vapor starts condensing into liquid water and forming that cloud. But it continues to rise up. And in some cases, these tops of thunderstorms can be 20, 30, 40,000 feet, maybe in extreme cases, 60,000 feet above the ground. In that middle section, we have the mature stage. In that stage, we still are having some updrafts that are continuing that thunderstorm development, but now we're getting to the point where we're starting to have precipitation. And with that, we're also having some downdrafts, some air that's sinking down to the ground. And then the third stage on the right-hand side is when that storm is mostly just downdraft. And since you don't have more air coming into it, it starts to die out. Another category that we can talk about are training multi-cell thunderstorms. Now, if you're just looking at one of these storms, it's going to look like one big thunderstorm. but actually these are made up of multiple cells, multiple thunderstorms, but they're all kind of clustered together. And in this case, what we're talking about are training multi-cell storms. And just like you would think with a train, you have one lined up behind the other. You have multiple cells lined up one behind the other. And what happens here is when one of these cells develop, part of that downdraft comes down and it pushes up air behind that storm and starts to raise up and create another thunderstorm. And so you can have multiple cells in various stages of development, all moving along the same path. With these types of thunderstorms, you can expect a lot of rain because it keeps moving over the same area. You can have some hail associated with it. You can have some lightning. You may have some weak tornadoes. Here's an example of what we're talking about with this. So you can see multiple cells here. And so this would be moving from left to right, if you're looking at the screen. And these are all moving over the same area. So you have multiple cells, just one right after the other. Another type of multi-cell line that I'm sure most of us have experienced are squall lines. Now with this one, instead of having cells one behind the other, you have multiple cells and they're all side by side and moving together. This is usually associated with the advance of a cold front. We did have some of that here in central Illinois last night in terms of a squall line moving through. And that gust front is that whoosh of air that comes through right before the storm hits. And that's a straight line wind. Those gust fronts can be anywhere from 30, 40, 50, in extreme cases, 70 or 80 miles an hour. With these squall lines, you can expect some intense rain, some hail, some lightning, and again, potential for weak tornadoes. Again, these usually form along or just ahead of a cold front. As that cold air moves along, that cold air is dense, it wants to stay close to the ground, and so it pushes that warm air that's in that area out up above that cold air, and that lifting can create those thunderstorms. Now, this is just an example again of what a sideways view would be of a squall line. You can see that incoming air, and once it gets up so high, it starts spreading out in all directions, and that helps create that anvil appearance to the thunderstorm. That anvil comes from those stronger upper level winds that push those clouds in the direction that those upper level winds are going. On the backside of the storm is where you have the precipitation and the downdrafts. As that air has, or as that thunderstorm has rainfall, that's also pulling down air with it to add to that downdraft. Once that downdraft gets down to the ground, it starts spreading out. Some of it starts spreading out towards the front of that thunderstorm, and that's where you get that gust front. If you see that little blue line out on the edge of that thunderstorm, that's indicating where that gust front would be. Again, just right ahead of where the precipitation would be. Typically with these squall lines, if you look over on the left-hand side, the heaviest rain occurs right when that storm first hits. And then you have lesser and lesser intensity to it as it continues to move along. Now, another type of thunderstorm that we can talk about, and this is one that a lot of weathercasters really don't get into much detail unless you watch the Weather Channel or some of the AccuWeather reports, is something called a mesoscale convective system. Again, this is a bunch of individual cells, but they're all clustered together, and they all kind of act in tandem with each other. Now, a mesoscale convective system can be a very large cluster of storms. It can cover an entire state. And one of the differences with these is that it can last for hours and hours. And typically, these types of systems are actually strongest during the night. They can produce really heavy rainfall. They can have a huge number of lightning strikes with them, and they have the potential for tornadoes. And I'm sure a lot of us have experienced those nighttime storms when they have just lightning all over the place. And again, there may be the occasional tornado warning that goes out with it. But the big hazards with these are large amounts of rainfall and that really dangerous lightning. Now, within that, there are actually some subtypes of mesoscale convective systems. And one of these is called a mesoscale convective complex. This is a cluster of thunderstorms. Again, it's a large cluster of thunderstorms. It's kind of in a circular shape. Again, this is something that can initiate or get going out of the remnants of some of those afternoon thunderstorms. That if they're still around in the late evening hours, maybe they're just hanging on, they can fire up again and they can become part of this mesoscale convective complex. The thing that really fires these things up and gets them going again is during the nighttime, as the ground surface cools off, there is a low-level jet, in other words, a kind of a stronger upper level wind that's about 1,500 to 3,000 feet above ground that gets stronger at nighttime. And it brings in warm, moist air that can feed into these thunderstorms and let them continue to get stronger. Here's a satellite image of one of these. And I know this is kind of hard to see here, but it's actually covering parts of 3 states. As it says up here, it's covering parts of Nebraska, Western Iowa, and southeast South Dakota. And again, you can see with that red, if you're familiar with some of the satellite imagery, that's really high cloud tops, which are going to be associated with really heavy rain in most cases. One other type of mesoscale system we can talk about, or that I want to talk about, is something called a mesoscale convective vortex. This is also a large cluster of cells, but in this case, these clusters of cells have all started slowly rotating around an axis. And even when those thunderstorms may die out, that rotation may continue. And if it continues long enough, it can actually fire up more thunderstorms the following day. And this is a slide showing some radar imagery and also some other weather data here. And if you can see the outline, this is dealing with more or less central Texas. But if you notice where the rainfall is at, right there in east central Texas, you can see it's kind of got a circular pattern to it. And if you notice the little blue lines and with the little, looks like feathers, it's showing the direction of winds. And if you look, it's got a rotating appearance to it. So this is a mesoscale convective vortex. So that entire cluster of thunderstorms is slowly rotating. The next type of storm we can talk about are supercells. These are the ones that you really have to watch out for. And while we do experience supercell thunderstorms in Illinois, we don't get as much of them as they do out in the Great Plains states, places like northern Texas, Oklahoma. I think Oklahoma City is almost a bullseye for these things. Kansas, Nebraska, those areas, they have a lot more of these. And they have a lot more of these earlier in the year than we do. But with these, an individual cell, an individual thunderstorm is rotating itself. These cells can be 5 to 15 miles wide. And again, these can have huge amounts of rainfall. They can have very dangerous lightning associated with them, which we're going to talk more about a little bit later on. They can have strong straight line winds. And these are the types of thunderstorms where you get the really damaging tornadoes, the EF3, EF4, and EF5 tornadoes taking place. And where they typically develop is along a boundary line that's called a dry line, which we're going to talk more about again here in just a little bit. Here's an example of what a supercell may look like. The tops of these thunderstorms, these are ones that can get up in the 40, 50, even 60,000 foot height range. So that's telling you there's lots of instability in that air. If that air can rise up to that altitude, there's lots of instability. And the more instability there is, the more potential there is for that being a damaging storm. Up in the very top of that thunderstorm, you can have a buildup of positive charges, which can create positive discharge lightning that we're going to talk about. You can have lots of cloud to ground lightning down at the base of that thunderstorm. And because this entire thunderstorm is already slowly rotating, if you get an area in that storm, typically on the backside of that thunderstorm where you're having the updraft and that updraft can get stretched out, it can increase the rotation to the point where you may have a funnel cloud tornado come out of it. So what is this dry line? What are we talking about here, and how does that allow a supercell thunderstorm to form? Well, a dry line is actually a boundary line between two different types of warm air. It's going to be a boundary line typically between hot, dry air that's come from the southwestern part of the US, and then that warm, juicy air that's come out of the Gulf of Mexico. So here we have a weather map. And if you're looking at this, if you see up at where that L is, that's a low pressure system. And you can see the red line out to the right of it, that's our warm front. The blue line with the triangles is the cold front. So everything between those two lines, between those two fronts, is where warm air is located. That's called the warm sector of that low pressure system. But you can have two different types of warm air. You can have that warm, juicy air coming off the Gulf. And over in the southwestern part of the US, you can have this hot, dry air coming off like the Chihuahuan and the Sonoran Desert. Those different air masses are not going to mix together because they're different densities. And so you have a boundary line between those two different types of air. And that's where that dry line is. And if you notice, there's another line that you'll rarely see on your local TV weathercasts, where it may be on there, but they don't mention it. It's typically a line, and I've seen it on local weathercasts where they have it in yellow. But in this case, they've got it as a slightly blue line with little mounds on it. And that's where a dry line would be located. Now, here's the reason it's called a dry line. Well, first of all, I'll show this. This is how this sets up. So ahead of that cold front, you have this hot, dry air brought in from the Chihuahuan Desert. You can see those county outlines for Texas. So this hot, dry air is brought in. The thing is, that desert is up at a high elevation. The ground level in those areas are 5 to 9,000 feet up. As that hot air gets drawn into Texas, it's not going to sink down to ground level. Hot air is already wanting to stay higher because it's less dense. So it's not going to sink. It's going to stay up at that elevation that it started out at. And so what happens is, underneath that, as that warm, hot air comes in, that juicy Gulf air gets stuck underneath it. That hot, dry air acts as a cap, though. As long as it doesn't allow that warm, juicy Gulf air to push up through it, you don't have thunderstorms. And that's why it's called a dry line. But if that air can eventually push through that, well, that's when Mother Nature opens up a can of, well, it opens up instability, which can create thunderstorms. Once that cap is opened up, the air can be rushing upwards of 150 to 200 miles an hour. As that air is rising vertically, air that's moving horizontally as it moves up can be moving in different directions, which starts that vertically, that rising air to rotating. And that's where that rotation gets going. Here's a satellite view of a dry line. Now, if you notice, we've got Kansas, Oklahoma, and northern Texas here. On the right-hand side, mostly clear air. On the left-hand side, like in central Nebraska, western Kansas, in those areas, pretty clear air. But we can see right where that dry line is at. It's in central Kansas, kind of west central Oklahoma, and northern Texas. If you count them, we have 1, 2, 3, 4, 5, 6, 7 supercells located there. And look at how large those cells are. Those aren't your little pop-up thunderstorms. Those are supercells. Now, we mentioned a little bit before about gust fronts. And I know that especially the folks that may be from Iowa or central or northern Illinois that are participating today experienced a very strong, long-lived gust front last August. Those are called derechos. We're not going to talk a whole lot about those today, but the whole concept of a gust front is pretty much the same. These are straight line winds. They're created from downdrafts within that thunderstorm that push out in front of the thunderstorm. These can be, in most thunderstorms, they can be 30, 40 miles an hour, but in some cases they can get up to 50, 60, 70. And when we talk about derechos, ones that can travel multiple states and last for hours, last year and some of the other ones that we've had in the past can get up to 80, 90 miles an hour, maybe even over 100 in some cases. Very damaging straight line winds. All right, so now we're going to switch gears a little bit and talk about lightning. Now, if we were all doing this face-to-face, I would take a little bit of time and ask the studio audience to share some experiences that you may have had with lightning, hopefully not bad experiences. But since we can't do that today, we'll just go ahead and move on into the discussion on this. In terms of where you're going to find the most lightning strikes, as you might expect, there's the greatest density along the Gulf Coast, and especially Central Florida. Central Florida has the largest number of thunderstorms for any state, and so just by that, you're going to have a large number of lightning strikes within that area. Besides the Gulf Coast, you have, again, Oklahoma, where you have a lot of those supercells develop. But you notice most of the Great Plains, most of the Midwest has their fair share of lightning strikes. If you notice on the Western coast, though, they have very few lightning strikes out there. Not to say that they have zero, but they have very, very few. So how does lightning form? And we'll not get into a whole lot of detail with this, but I'll just try to go through some of the basics with it. In a thunderstorm, you got a lot of turbulence. You got air that's rising up. You got little pieces of ice in there. You got water drops, and they're all banging together. And sometimes when that ice collides with water, it creates this kind of semi-soft material called graupel. So now you have ice, you have this graupel, you have water particles. As all of these things bang into each other, you get electrons, you get charge that's transferred between particles, and that graupel becomes negatively charged. It's really not that much difference than if you rub your shoe across the carpet and you get that static electricity. Kind of the same concept. Now, I should mention here, we're just talking about cloud to ground lightning. As that negative charge builds up in the bottom of that thunderstorm, in relationship to that, you have a positive charge induced from the ground. Now, as that charge develops, that doesn't automatically mean you're going to have a lightning discharge. You can have a buildup of up to millions of volts of electrical field there. But the air is a very poor conductor of electricity. And so before that discharge of electricity occurs, it has to have a pathway, an ionized pathway that's created from the cloud to the ground before that electricity will flow through the air. And that pathway is called a stepped leader. Now, just like this slide that we're showing here, and you look at that lightning bolt in the background, and you can see it's got all these zigs and zags in it. That was that pathway that was created before that electricity actually discharged. That all happens in fractions of a second. You're not going to see that step leader forming because it happens so quickly. But it starts from the cloud, and again, it's following that path of least resistance. Once that step leader from the cloud gets to within a couple of 100 feet of the ground, there's a positive leader that starts from the ground and works its way up. And then they meet. Once that occurs, you have that negative discharge, and then you have a return stroke. That's going to be the brightest part of that electrical discharge, that lightning strike, is that return stroke. Have you ever noticed that it seems like lightning flashes? You know, you'll see that lightning bolt and it looks like it flashes 3 or 4 times. Well, probably in that same instance, it may have discharged up to 12 times, but our eyes and brains can't keep up with it because it's happening so quickly. We may only see it, what appears to happen 3 or 4 times. It may have happened many times more than that, but we just can't, our brains can't keep up with that. Each one of those, again, only lasts about 30 microseconds. Very short period of time, tremendous amount of power associated with these though. Now that's cloud to ground lightning. That's the most common form of lightning that we experience. There's also cloud to cloud lightning. But another type of lightning that I want to visit with you about a little bit, and this one is far more dangerous. This is, again, one that is very common in supercell thunderstorms, is something called positive discharge lightning. I don't know how many of you have ever heard of a term, a bolt from the blue, where there may not be a storm close by, but then just all of a sudden you get a lightning bolt. More likely, that's that positive discharge lightning. This is actually coming from the top of a thunderstorm. Now, if you think about this, again, the tops of these thunderstorms can be 30, 40, 50,000 feet up. They've got a lot more air to go through, so they're going to have to build up an even greater amount of electrical voltage, electrical field there before you have that discharge occur. So these are much more powerful. They also last longer. And these are ones, especially that happen out west, create a lot of wildfires because these discharges can occur up to 10, and in some cases I've seen recently where they say that they can occur up to 15 miles away from where the thunderstorm is actually at. And if you have one of these lightning bolts hit a dry area, dry grass or whatever, starts a fire, and that storm is nowhere close to put the fire out, that's how a lot of wildfires start out in the West. Naturally, is through this positive discharge lightning. Another type of lightning, now this is something that I have not experienced. For some of my classes that I teach, I also teach for a community college. I've had some say they've actually seen some of this, is something called ball lightning. Now again, this is very rare to occur. It is a real thing, but it's really freaky. There are stories where you have this kind of discharge coming out of an electrical outlet or something like that into a house, and then you just kind of have this ball of plasma that's around, floats around for a few seconds, and then just kind of pops and dissipates. Nobody really knows exactly what's causing it, but one of the most recent theories on this may be because of the electrical potential that's present in thunderstorms, that maybe some of the dust and particulate matter that's in the air at the time, if there's a concentration of it, it may get vaporized from some of this electrical discharge that's occurring otherwise, and that may be the cause of it. Again, that's just a theory. Now, here is one I hear a lot of people talk about, and again, this was something I grew up with, but I want to put this one to rest. Probably a lot of folks have heard of heat lightning, where you're out on a warm summer evening, you look way off in the distance, you see flashes of light, And folks will say, well, that's because it's a warm summer night. Lightning is not caused just because it's a warm summer night. There are thunderstorms out there. We have to think about what we live on. We live on the curved surface of the earth. There can be thunderstorms 100 to 150 miles out. On that curvature, we may be barely even able to see the tops of those thunderstorms if they're that far out. We're certainly not going to hear it. We're certainly not going to see the actual lightning bolts in those storms. But what we may see, if it's fairly clear in between our location and where those storms are at, is that ambient light that comes off of that lightning. And so, is heat lightning caused by heat, or is there such a thing as heat lightning? No, it's regular lightning. It's just too far away for us to see, too far away for us to hear. Tell your friends and neighbors. Another interesting type of electrical discharge that occurs way above where the thunderstorm is actually at. There's interactions that occur in the upper parts of the atmosphere. Now, I've never seen any of these things myself, but we've actually have some photographs of these. And actually, I think there was a NOVA episode a few years ago where back when it was either from the space station or maybe even when the space shuttle was still around. But there were some astronauts that actually photographed some of this from up above where this was even occurring. But if you look at the thunderstorm itself, you can have more or less, well, if you're a Star Wars fan, think of those lightsabers. You can have something like that shooting out of the top of the thunderstorm. It's called a blue jet. Even higher than that, again, if you look over to the left, we're talking about 50, 80, 100 kilometers up in the air. So we're talking about 40, 50, 60 miles up. We're getting to the very edge of space with this. But there are electrical occurrences that occur, interactions with some of the gases in the atmosphere at that elevation that are called sprites. They're kind of reddish in color. And then at the very edge of space, you can have this circular or halo a discharge called elves. Here is an actual photo. This is from the Gemini Observatory in Hawaii. But you can see that blue jet shooting out of the top of that thunderstorm. And then above that are some of those red sprites. Very cool. I know I got to get a life. Now, as research continues with lightning, we're finding out that there's a lot more to lightning going on within the thunderstorms than what we may observe. You know, we think of that lightning bolt as a one-off situation, that it's just that and nothing else. But within that thunderstorm, that lightning bolt can be part of a much larger electrical discharge that's all kind of combined together. And in fact, the longest lightning strike or the longest lightning discharge on record is from a bolt in Oklahoma in 2007 that stretched over 200 miles in length. The longest lasting lightning discharge ever recorded, again, showing that one lightning bolt can be part of a much larger discharge, is a flash that occurred in France that lasted almost 8 seconds. So we're finding out a lot more about lightning and what it's doing within these thunderstorms. One of the other things that has been found recently is that some research is actually showing that as lightning occurs in particular areas, it's actually kind of good for space exploration, because what it does is it helps clear out some of that more dangerous radiation in the very lower parts of space where we have a lot of our satellites in the space station. So in that regard, that lightning helps us out in terms of having those satellites and actually being able to orbit the Earth with people. Now, where on Earth is the largest density or the greatest density of lightning? It's Lake Maracaibo in Venezuela. Over 233 flashes per square kilometer. This is also an area that is very swampy. And in swamps, you can have swamp gas, which is methane. And so there are videos out there you can probably go online and see at nighttime when there's thunderstorms. It's quite the light show in that area, not only because of the lightning itself, but then also because of some of the swamp gas in this area that can add to that. Now, as a lightning bolt occurs, it superheats that air to over 40,000 degrees Fahrenheit instantaneously. And what it does is it creates a shock wave. And some folks you may have heard some folks say, well, I was knocked down by a lightning bolt. Well, that person wasn't hit by lightning itself, but probably if they were within 10 to 50 feet of a lightning bolt, they may have been knocked down by the shock wave. Just like you, when you maybe seen pictures of bombs going off and you see that wave going out from it, same thing happens with a lightning bolt. But as that shock wave moves away, it quickly disintegrates as it moves through the air and becomes an acoustic wave, which we know as thunder. And hopefully that didn't scare folks, or hopefully it wasn't too loud. I tried to turn down the sound ahead of time, so if it was too loud, I sincerely apologize. Let's talk a little bit about thunder, though. Sometimes you hear that crack or that really strong, almost instantaneous sound. That's going to occur when you're very close to the lightning and that sound wave has not disintegrated very much. Other times, when the storm is off in the distance, you hear this gentle rolling and rumbling of thunder. Now, what causes that? Well, first of all, we have to think about the speed of sound. We see that lightning bolt almost instantaneously because it's traveling close to the speed of light, which is about 186,000 miles per second. So again, we're going to see that light almost instantaneously. Speed of sound is only about 1/5 of a mile per second. So if you think of a lightning bolt from top to bottom, maybe 10,000 feet from top to bottom, what are you going to hear first? You're going to hear the sound of that flash from that flash that's closest to you. It's going to take a little bit of time for that sound from the top of that lightning bolt to reach your ears. So it's going to stretch that sound out. The other thing that happens is that sound is going out in all directions. And so it may go out, it may bounce off of other objects or clouds, and then come back to you as an echo. So that's where that rolling and rumbling comes from. Now, a little rule of thumb with this, and probably a lot of you are already familiar with this, but since we know that sound travels 1/5 of a mile per second, you can pretty well figure out how far away the lightning is. If you see the lightning flash and then you count off 5 seconds, that means that lightning is about a mile away. And that's pretty darn close. If you're outdoors, you'd best be getting indoors. Again, that lightning bolt itself, very small, less than 1 inch in diameter. Tremendous amount of power with this. Each one of a flash can be up to equal to a 1 kiloton explosion. Tremendous amount of voltage with this, hundreds of millions of volts, but the more dangerous part are the amps. It can be from 10,000 to 200,000 amps. How much does it take to kill human? A lot less than that. A few lightning facts to go through. There's about, on average, 25 million cloud-to-ground strikes in the US every year. Number of lightning deaths in 2020 was about 17 nationwide. And this is really good, not for the fact that there were fatalities, but the fact that that number has gone down tremendously. If you would have looked at this back in the 1990s, it was up closer to about 65 to 70. So I think people are a lot more aware of what they need to do when a thunderstorm is approaching. And like I said before, lightning is actually a big natural culprit of wildfires in the United States. A little bit on lightning safety. Again, if you can hear that thunder, you're close enough to be struck. And I know we're all guilty of sometimes staying out a lot longer than we should, but we really need to try to be on the safe side with this. If you're outdoors, find shelter in a grounded building. A baseball dugout is not a safe place to be. An open pavilion picnic area is not a safe place to be. You'd be better off to be in your car with the windows rolled up. And it's not the rubber tires that protect you, it's the metal cage of that car. So those of you that own Corvettes might want to look at a different vehicle for that. And talking about telephone lines, and probably some folks don't have those lines anymore, but if you have a hardline telephone in your house, those can conduct electricity. Plumbing can conduct electricity. I had one story of a student a few years ago that they said when they were a little baby and their mom was giving them a bath, lightning hit not too far outside, traveled through the metal plumbing, and actually zapped them a little bit. If you're around a bunch of trees and you can't get to a shelter or a car or anything, try to get under the shorter trees, because the taller trees are going to be more conducive for that step leader to try to find a pathway. If you're out in water, get out of that water. Water is a great conductor of electricity. It can travel a long, long ways. If you can't make it to land, crouch down in the boat. Try to stay away from metal if possible. If you're out in an open area and you can't get to any other thing, what you want to do is find an area that's not going to flood. You don't want to lie completely on the ground. What you want to do is squat down on your feet as much as you can. They've kind of changed this. Back about 20 years ago, what they said was try to get on the balls of your feet. Now, how in the world is someone going to try to squat down on the balls of their feet, probably with the wind howling around them, and continue that? As I've gotten older, I'm much better with just trying to squat low on the ground. Again, you don't want to lie flat on the ground. If you're doing that and that surface is wet, lightning hits close by, you've got half of your body in contact with the wet surface. All right, talk a little bit about tornadoes. Practically every state has had a tornado. Now, for this one, you'll see a few states that show 0, but that's just for that particular time frame. Actually, if you go out over a longer period of time frame, every state of the United States has experienced a tornado. You can see that on average, again, for this reporting period from 91 to 2010, the average annual number of tornadoes in Illinois was in the mid-50s. You think, oh, that's a lot, but Illinois is a long state north to south. Doesn't mean those tornadoes were on the ground for any length of time. But we do have our fair share. And as you might expect, Texas being a very large state, being an area where there's lots of storms, and particularly supercell storms, they have a large number of tornadoes. But you also look at all those Great Plains states, Oklahoma, Kansas, Nebraska, the Dakotas. They have lots of them as well. One that I was a little surprised about is Colorado. Colorado also has a large number of tornadoes. And this just shows from last year, from January to the end of 2020, reported tornadoes throughout the United States. Again, you can see how they're clustered in the southern states, along the eastern seaboard. And you notice there's quite a few in the northern part of Illinois for this particular year, for 2020. And whether that's because of it being more densely populated, more people have seen tornadoes to report them, although a lot of them are radar indicated as well. We're not the only ones that have tornadoes. Europe also has them. You can see almost every continent has it except Antarctica. Very few in South America, small area there, small area in Southern Africa. Australia has a few. Even Asia has a few. We're really, though, conducive to having the largest number of these simply because of our geography and the fact that we do have this warm, moist Gulf air that can easily come in and right next to this hot, dry air coming out of the southwestern part of the US, which can in turn create a dry line, which in turn can create supercells. Excuse me, to just talk a little bit about some of the research with tornadoes. This is some information from University of Illinois, and this is from Dr. Jeffrey Frame. One of the things that they had seen from some of his research and the group that he has worked with is that air that's coming out of a storm, if it's not very cold relative to the air surrounding that storm has a better chance of producing these stronger tornadoes. So in other words, the downdrafts, the air coming out of that storm, if it's about the same temperature as the surrounding air, there may be a better chance of the bad tornadoes forming. And again, what's happening with a tornado? What is creating that funnel? Is there one answer for this? No. And they're still doing research trying to find out what these mechanisms are. But one of the things that does appear also is that if you have a rotation from aloft that's brought down to the surface, as it gets pulled up into an adjacent updraft where the air is going back up, if it can stretch that rotation out, kind of like when you have the figure skater, when their arms are stretched out and they bring them in, what happens to their rotation? It becomes faster. That's what kind of can happen maybe with these tornadoes. And that's what brings that rotation that's in the cloud, in the thunderstorm, down to a tighter spiral that can end up reaching the ground as a funnel cloud. Different types of tornadoes we can talk about. Those typically created from non-supercell thunderstorms. The entire storm, as we said before, is not going to be rotating. That rotation can occur a little bit closer to the ground. And typically with these, you have a smaller, narrower funnel associated with it. You may see some of these from time to time. Again, they're very thin. They typically don't last long. Gustnadoes, land spouts, water spouts. With the EF scale, we're talking about EF0, EF1 types of tornadoes. And actually, when you look at the majority of tornadoes, the vast majority of tornadoes are in these really lower end categories, the EF0 and the EF1s. When you start getting into the more powerful ones, the EF3, EF4, EF5, EF5 tornadoes, very rare. But we're going to hear about them more because they're much more damaging. Squall lines, as we said before, can be associated with tornadoes. And part of the process that's occurring there is when a squall line moves along, sometimes the middle part of that squall line will bow out. And when that's shown on a radar, it's called a bow echo. So as you look through the different progression of the bow echo in this case, when you get into the C and the D category, if you're looking at that, you can see how that bow how that squall line is bowed out. And so what happens is on each end of that bow, you have the air starting to swirl around on the ends of it. And that rotation may end up creating a weak tornado. The supercell tornadoes, again, occur when you've got the entire updraft in that storm already slowly rotating. When we have these really large thunderstorms, these EF3 to EF5, in some cases they talk about a tornado being a mile and a half wide. If you were able to actually look inside that tornado, what you would probably find or likely find is multiple funnels, multiple vortices, and they're all spinning around each other. You're not going to be able to see that because of all the debris in that area. But more than likely, what's happening is you've got multiple funnels, multiple suctions in there that's occurring. And as we get more and more pictures and videos of tornadoes, we can start seeing some of that. And again, these multiple vortices, these multiple funnels, are all spinning around together. So you've got the funnel, and then they're all spinning around each other. And here's an example where we have pretty good sized funnels next to each other, and think about them spinning around each other. Here's another example where you've got a fairly large funnel next to a smaller one, again, spinning around each other. And that would also help explain in some cases, and you probably heard multiple stories where in neighborhoods where a large tornado has gone through, and maybe a house or multiple houses on one side of the street got completely blown away, while a house or multiple houses on the other side of the street may have just got roof damage. Well, it may have depended on whether one of these vortices, one of these actual funnels, directly hit a home. If you've got a funnel that's maybe blowing at 150 to 200 miles an hour, that's going to cause a lot more damage than wind that's maybe only blowing at 80 miles an hour out away from where that actual funnel is at. So where one house may get roof damage, if an actual vortice, an actual funnel hit, you may have more damage. Some of the other research, and there's lots of research going on. Please don't pay any attention to that movie Twister from 10 or 15 years ago. Very little is very accurate in that. I know it's entertaining. I've watched it a time or two, I guess just to see the cow fly through the air. But one of the things that's going on now, and this is actually from University of Colorado, and there's other places that are doing this, but they're using drones, multiple drones, flying these not within the storm itself, but adjacent to the storm to get information. And you've also seen the mobile trucks where they have the mobile radar and those types of things. That's also being done a lot. And one of the things, this is some research that I just saw the other day from University of North Dakota. Again, what causes that air to spin faster at lower levels where the tornadoes form? And one of their thoughts is that there's a sudden drop in air pressure, drawing in and concentrating that rotating wind. Again, there's really no definitive answer yet on a mechanism, and in my opinion, there's going to be multiple mechanisms involved. But one of the other cool things that they were able to do with this is they actually compared some of the actual observations and then compared that to what a computer model would show. And it showed, you have, if you look in the upper part of here, you see the funnel associated with the tornado, but then you also see a narrow area where you have, another narrower rotation associated with that. Very cool. Oops. So for University of Illinois, one of the things that they have found, and I just saw this recently as well, is they've looked at weather occurring way before a tornado outbreak. And they said that persisting weather patterns, something lasting longer than 3 days. So for example, if you have abnormally warm, very abnormally warm weather, sticky weather, multiple days in a row, that seemed to contribute to a greater percentage or greater likelihood of tornado outbreaks. And they developed a model to try to analyze this. And it's shown some really good accuracy with it, even up to 3 weeks out. Now, is that going to say you're going to have a tornado at such and such time on such and such day? No. But what it can say is there's maybe a greater likelihood of tornado activity out ahead of time. All right, just some quick observations. Some of you already may be weather observers. One of the things to look for is something called inflow bands. If you're looking at this picture, if you look at the left-hand side of it, you see that area of clouds. That's very strong wind that's coming into that storm. That may be an indicator of where a tornado may start to form. Another one is called a beaver tail. And again, you can see this beaver tail cloud formation. The other thing to realize, though, is sometimes your eyes can be very deceiving. What may look like something like this may not be the case. So you have to be really careful sometimes. One of the other things to look for is this wall cloud, this drooping cloud. And if you notice it and you see that it's spinning, that is a really good indicator that there may be a tornado that may form out of that. And that, folks, is the presentation. I think we do have a little bit of time for some questions, so I appreciate everybody's attention. And do want to mention before we get to the questions, we do have a survey that if you would take the time to complete it, it would be much appreciated. Next month, our Everyday Environment webinar series will be held on April 8th. And for that one, Extension Educator Peggy Doty is going to be talking about owls. So be sure to sign up for that one. And you can go to go.illinois.edu/Everyday Environment webinars to find more information on upcoming webinars. So with that, Aaron, I will let you, if there are any questions, go ahead and shoot them to me and I'll try to answer them.
Yes, thank you so much, Duane, for sharing with us today. And thank you everyone for joining us. We have a couple questions. If you do have a question, please enter it into the chat box now. So this question was asked early on, and I believe you've answered it, but just to clarify, does a storm have to have lightning to be a thunderstorm?
Well, technically it would, because if you have to have thunder to have lightning. So, and a lot of times we use the term thunderstorm very generally. But, if you want to get technical, would it be a thunderstorm? No, because if there's no lightning, there's no thunder. In that case, I guess we would just call it a heavy rainstorm.
Great, thank you. We have a few questions about tornadoes. Is there an average speed of tornadoes?
Well, if you're talking about ground speed, as it moves across the ground surface, typically they're in the range of about 15 to 20 miles per hour as it's moving across the land surface. In terms of wind speed within the funnel itself, like I'd mentioned before, the majority of tornadoes are in that EF0 to EF1 category. So somewhere around 80 to about 110 miles an hour. Still enough to cause damage, but nothing compared to an EF5, which may be upwards of 250 to 300 mile an hour. The highest recorded wind speed in a tornado is 318 miles an hour. And we have to think about the velocity of air and the damage that it causes. If you're comparing a 100 mile an hour wind to a 300 mile an hour wind. So that 300 mile an hour wind is 3 times faster than 100 mile an hour, but it's going to be 9 times stronger. So that's why you can see things like pieces of wood being impaled into concrete and those types of things. And why it's very necessary for you to protect yourself if you're out in an area and can't get to shelter. You need to try to protect your head and body as much as possible. Good question. Great,
thank you. Do tornadoes spin in both clockwise and counterclockwise directions?
They can. And I was going to mention that with those bow echo initiated tornadoes, if you noticed, the rotation associated with those were in opposite directions. So yeah, it can happen with that. The Coriolis force, because you're talking about a pretty narrow area in most cases, doesn't relate as much to tornadoes as it would to a hurricane or a large area, low pressure system.
Okay, great. We will do one last question since we are almost at 2 o'clock. Is there any research on increasing or decreasing frequency of tornadoes or changes in severity with climate change?
Well, as first on the climate change, there is research being done on that, but it's kind of it's almost like with hurricanes. There's some things that show it being stronger, some of it being weakened. So you've got some offsetting things going on there. What may happen is the number and frequency of tornadoes may shift. They may shift farther north, and that's to be seen yet. But in terms of the number of tornadoes and the intensity, I've not seen a lot of research to say that tornadoes will be more intense. but where they are located may change. And it may move a little bit farther north than where it's currently situated. And then in terms of trying to change the number or intensity of tornadoes, there was some research that's been done dealing with cloud seeding and those types of things. And it's kind of like with hurricanes. They really haven't seen any big change associated with that. And one of the things with tornadoes is because they occur, again, the lead time for even tornadoes from the time they're seen to the time it hits an area is about 13 minutes on average. So they occur very quickly. They kind of occur, even though we know that there's a likelihood for tornadoes to occur. To get that actual funnel to occur, we don't know ahead of time where that is exactly going to happen. So, to try to contain those really isn't in the realm of possibility at this stage. Good questions.
Great, thank you, Duane. We are a couple minutes over our time, so we will stop there today. Thank you, Duane, so much for a wonderful presentation. And thank you everyone for joining us today. Make sure you sign up for additional webinars and fill out the evaluation that Duane has for today's webinar as well. Take care, everyone.